actually reduced. It's not 2 anymore because you don't have a uniform source anymore, uniformly distributed source anymore. And this turns out to have an entropy of 7/4 bits per symbol. So it's slightly less than 2. So there exists something else there, some code, some magical code that allow us to do close to 7/4 or less than 2 bits per symbol. Okay? So in this case, if you 2 bits per symbol, you're wasting your bandwidth. Okay? Now, before we talk about variable length code, let's take very little time to talk about fixed length. Okay, fixed length means this. You use the same number of bits to encode your sequence. Okay, this is the trivial and very simple things to do. But sometimes it actually has a lot of practical application. For example, our email, when we communicate through email, we're using the ASCII code, okay, which use 7 bits per character. Okay, so that is a fixed length code. Okay, and sometimes on the product that you see in the supermarket, you have those bars. Okay, those are called UPC or Universal Product Code. That's fixed length code. Okay, now in those cases, you don't have a lot of bandwidth, all right? Because you don't have millions or billions of products in the store. You only may have 1,000 or so. So it's easy to use fixed length code, and we don't have to use compression, right? Now, so an example would be BSBSS in ASCII code. Okay, will look like this: 68, 83, 80, 83, 83. That's in decimal. Translated in binary, it will look something like this. And so if you actually type BSBSS in your email and send it away, there's a body of your email that looks like this. Okay? Because that's just automatically translated to binary code sent over communication channel. Now, the advantage of this type of code is that it's very easy to decode. Right? All you have to do is to do table lookup. You read 7 bits, you do table lookup, you output a character. Okay? So that table looks something like this. Okay? And it basically go from 0. Okay. Now, why do we need 7 bits? Can we do it with how many alphabet letters do we have? 26, right? We have 26, right? So why don't we use 5 bits?
Because there are many symbols, many other symbols.
Exactly. We have question mark, we have punctuation, we have comma, we have capital. Okay? So we automatically go above 32. Okay? And then we have numbers. So by the time you add all these things up, we're above 64. If we're above 64, the next step up is 128. And so we have a few extra symbols that we rarely use in email, but it might be used by your printer, for example. Okay, some of the control, okay, for example, right here, are not being used for symbols, but they are being used for other purposes by the computers. So it turns out that we need 7 bits. Now, the main problem with fixed length codes is the inefficiency, right? Because with fixed length code, you can never realize anything close to the entropy, okay? Because you are forced to use the same amount of code for an unlikely event as well as a very likely event. If you have a lot of likely events, you will automatically lose out, okay? So what we need to do is to use something called variable length code. And the main idea is this, and it's very intuitive. We need no math whatsoever to recognize this, right? We have to allocate shorter length code words to symbols that occur very frequently. Agree? Something that occur very, very frequently, and if you want to minimize the average, right? You want to assign very small, very short code. And for something that occurs rarely, then we can afford to use long code. Okay? So this is certainly more efficient representation, and it's very good for compression. There are 4 different types of variable length codes that I want to just go quickly over. The first is Morse code. You heard of it before, right? For telegraph. Okay? And then Shannon final code, Huffman code, arithmetic code. Okay? Now, for Morse code, it's being designed. The first successful public demonstration took place in 1844 between Washington, D.C. and Baltimore. And this is the message being sent on that day. Okay, that's what any Catholics in here. This is a phrase from the Bible. Okay, and what Morse did. Okay, Morse is an American engineer. What he did is he assigned these things. Okay, E has a dot, and you can call it 0, right? And T has a dash, you can call it 1. Okay, so as you can see, T is very in the English language. T is very common, and E is very common. Okay, so they get assigned very short code word, but then things like Q or X or Y or even B, okay, get assigned very long codes because they are a lot more rare to encounter in practice. So this telegraph is simply a binary communication system where dash, you can think of a dash as 1, dot is being 0. What really happens is there's a human operator sitting at the transmitter, and there's also a human operator sitting at the decoder, okay, to automatically encode and decode all this, okay? So if you press this transmission for a long time, it will give you a dash. And if you tap it very quickly, it will give you a bunch of dots, okay? So this is, so it will come out like this, okay? There's an iron piece, a pen, there's a coil, and if you connect the transmission key right here, you will generate a magnetic field, which will turn into a magnet, will pull the pen down, and then you're going to write onto the little piece of paper here. So this is a dash, this is a dot, this is a dash, this is a dash, okay? And you have human operator to interpret this, okay? Now, can you think of anything, what if we want to use Morse code for digital communication without human operators, okay? Using computers only. Is that a problem? What kind of problem are you going to run into if you try to use Morse code?
Because there may be a mistake that we cannot determine if it is N or TE.
Exactly. There's what you call that, a confusion in the decoding process, right? How did we get away from that? The example that I have is SOS in Morse, okay? Now, where's S? S is dot, 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 O is dash, 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 and another S is dot, dot, dot. This is the most famous Morse message that you will ever see, right? This is probably coming out of the Titanic in 1911, right? 000111000 means major problem, okay? Now, so the Morse code for SOS is this, but there are actually several different ways to decode this message. It might be SOS or it might be BMS, okay? Because B, do I have B here? Yeah, B is dot, 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 dash, okay? And then M is dash, dash, okay? So there's a major confusion problem if you try to do this with the computer, okay? So that motivates the people when they first start studying information theory, okay, systematically, automatically recognize this problem, and they want to come up with something they call instantaneously decipherable, okay, which is the ability to decipher